Hello everyone, I'm Aysun. I'm leader of the team 22, and today we're going to present our final project video. As mentioned, we're making a 50 watts smart solar panel system right now. You can see our updated test distribution in here. As you can see, I handle managing, Humeria is our system engineer, Sheval does software, and Mariam handles hardware for this project. We followed our project calendar very strictly from March to May, as you can see, and in our project plan, we detailed every step and kept our total cost very low, like around $11, as you can see in here, while completing all these tasks on time. Our research and survey showed us that dual axis tracking is the most efficient one, actually. But in our comparison chart, you can see that we choose LiDAR sensors because they offer low-cost simple circuits while helping us to reach 90% alignment success. Per our project requirements, the system is under 6 kilograms, uses an ESP32 module for mobile control. And our objective theory focuses on to balance this high efficiency with low weight, low cost, and smart features.
Hi, I am Hümeyra Özyalçın. I am a system engineer on this project. The concept table shows our design decisions. For our system, we selected dual axis motion, a bifacial panel with flat geometry, LDR-based tracking, Wi-Fi and Bluetooth, SP32, lithium iron phosphate battery, and a servo motor. And the design meets all 4 environmental criteria: wind, water, dust, and temperature. Every choice is data-driven. SP32 scores a perfect 5 in processing power, Wi-Fi in data transfer, lithium iron phosphate in battery life, and R form factor in durability. Level 0 is the black box design. Solar radiation and environmental factors enter the system. What comes out is usable power: 5 volt USB, 12 volt DC, and 220 volt AC. Moving to the level 1 design, we'll look at the functional blocks. The panel sends raw power to the charge controller, which charges the 12-volt battery. From there, power flows to 3 outputs: the inverter, the power distribution unit, and the display. In the level 2 design, we go down to the component level. The blocking diode prevents reverse current, the storage protector handles voltage spikes, and the charge controller runs the MPPT algorithm for maximum efficiency. The BMS protects against overcharge and thermal runaway. The inverter produces a clean 220-volt AC sine wave, and the PDU delivers individually protected output through relays and fuses.
Hi, I'm Mariam Bülbül, and I'm the hardware engineer for this project. We compared our prototype against 2 commercial systems as shown in this slide. Our system weighs and costs significantly less than its competitors. It's also easy and quick to set up, making it highly advantageous. The flowchart starts with a mobile connection check. If there is no connection, the system has the ability to operate in offline mode. If a connection is established, the user can choose to operate the system in either automatic or manual mode. In automatic mode, the LDR sensor values are read and compared, and the panel is repositioned accordingly. Energy is then generated and logged. In manual mode, the user sends coordinates directly from the app, and the whole comparison step is skipped. There are also interrupt mechanisms for different types of faults. Non-critical faults trigger a warning notification, while critical faults shut the system down. The activity diagram illustrates the same system behavior using forks and joins. Forks represent simultaneous actions running in parallel, while joins merge them back into the flow. This slide presents a summarized version of our test plan across 4 categories. In unit and module tests, we verify individual components. In functional tests, we confirm app-based manual control and live data display. Finally, integration tests validate the complete system. Again, this is a summarized version of our test plan. The detailed test plan can be found in our report.
Hi, my name is Sheval, I'm software engineer, and I'm going to talk about the detailed design, risk management, system safety, and cost analysis. I will start with risk assessment metrics. The risks were analyzed based on their impact and likelihood levels. The most critical risks include structural failure caused by extreme wind load, Wi-Fi communication failure, and servo motor mechanical jam. In addition, software glitches, panel shading, and dust accumulation were evaluated as medium-level risks. These analyses helped us identify which parts of the system require additional protection. In this section, I will explain the mitigation and contingency strategies for these risks. For example, when strong wind is detected, the system to automatically switch into a safe horizontal mode. In case of servo motor jamming, the motor current is immediately cut off to prevent hardware damage. If Wi-Fi communication fails, the system continues operating autonomously offline while storing data locally. Various protection mechanisms have used in order to increase system reliability. This section, I will explain the project constraints and compliance requirements. Economically, the total system cost was targeted to remain below $80. For environmental sustainability, recyclable aluminum structures and long-life LiFePO4 batteries were selected. The system was also designed with a modular structure to simplify maintenance and part replacement. In terms of safety, low DC voltage operation was preferred, and compliance with CE, RoHS, IEC, and IP54 standard was targeted. Finally, I will explain the cost analysis. The main components include the ASP32 development board, bifacial solar panel, LiFePO4 battery system, high-torque servo motors, and environmental sensors. The estimated total prototype cost approximately $79.
Finally, our commercialization plan targets industrial weather stations and educational kits. In the future, we plan to combine all these parts onto one single PCB for the market. To wrap up, I would like to note that we use AI tools to assist in refining our presentation and project planning. Thank you for watching.